So I'm going to keep this period of time where I walk into the field of view of the camera because I think it adds an element of humanism to it. So I want to take a second to talk about complex hierarchies, and specifically why you would use a hierarchy type of model to view a complex system, and why that's realistic in terms of things like biology, chemistry, things like that. So a complex system, well, you got to start out with the idea of what's complex. So there's a lot of disagreement on a working definition of complexity in various fields. So I'm not actually going to try to define complexity. I'm just going to tell you what I view the word as, and that's going to change the way that you see what I'm talking about. So, so I'm just going to say that something that is complex is something that is constructed with components. And every bit of that phrase is important. So when I say constructed, I mean with structure, construct. So I mean that there is organization in this complex system, and it is important. So the word constructed is absolutely crucial to the definition. With components, components put together, component, pone. That means that the separate things are being put together. So we can kind of get a rough idea, kind of just fumbling idea of what complexity might mean. It's not a very precise definition, it's very vague, but in a lot of ways that's actually better for me. So let's get right into it. So let's say that I have a system. And a system is just going to be some organized object or group of objects. And the fact that it's complex means that it's constructed with components. So I have some system S that is constructed with the following components, R, B, and G. And for all intents and purposes, this is isolated from the universe. There's nothing outside of this. So we're going to talk about what is important in talking about my system S. So as mentioned in the paper I recommended last time, Architecture of Complexity by Herbert Simon, one important property that we need to pay attention to in our system is how much each of these states depends on each other. So what do I mean? What I'm talking about right now is near decomposability, just so if you're following my bullet points. So what do I mean? So if, let's say that blue, B, is in some state 1, okay? And when I say it's in a state, maybe it just means that, maybe we can just say it's on or off. We'll say that 1 equals on and 2, or 0 equals off, okay? If red depends strongly on blue's state, let's say if blue is on, then red has to be off. If those two systems depend on each other, then the total number of possible configurations for S, which keep in mind is composed of the states of R, B, and G, the total number of possible states for S goes down, okay? So what do I mean? It's, if I say that this has to be true, then it's impossible to get the state B equals 1 and R equals 1. That can't happen. So if these systems are all strongly dependent on each other, then it reduces the number of possible states that my larger system could have. And when I say larger, I just mean more abstract. So let's take this to a little more concrete example. So let's think of each of these as ants, and you know, we're not confined to just 3 ants. You know, this could stretch on forever, but these are the ants, and let's say that S is my ant hill. So if each of these ants can only do exactly what the other ants are doing, like in the extreme case, we could think that the ants could only walk in the same direction. They don't even have independence of motion. They can only walk together in single file. That wouldn't be a very complex system. There's only one thing that it can do, and that's walk. If you allow the ants to walk in different directions, of course, you get something a little weirder, but what we see in most anthills is that ants don't just, you know, walk in different directions. They actually do different jobs based on what the ants around them are doing. So let's say I've got my anthill, and a certain percentage of them are, we'll call them red. A certain percentage of them are foraging, okay? And then a certain percentage of them are building the anthill, tunneling, doing whatever. The dependence of these individual systems of ants can't be too strong, because if it is, then we've got a simple system. So when we say something is nearly decomposable, what I mean is that we have every reason to believe that R is actually a separate system from B. These two are not intrinsically connected. When they communicate, they do it through the overall action of the system. They, on average, might know about each other, but they can't directly influence each other. That's important, because if they did, then we might as well just write this all as one big box. But we can't do that, so I'm going to get rid of this because that's bad. Okay, so that's the idea of near decomposability, and kind of an idea of why it's important. There are a lot more reasons that it's important, and when I go into how robust a system is, you'll see that near decomposability has a huge role, because let's say I destroy G. If I destroy G and then that destroys B and R, then I've destroyed my entire system. But if I kill one ant, it doesn't necessarily strongly affect all the other ants in the colony. The colony will still survive. So near decomposability, very important for complex systems, and definitely something to think a long time about. Now, let's talk about how many of these components I need to account for in order to have a complete description of my system. So let's think, first off, I choose all of these words on purpose. Complete. I think components. So when I describe my system, I am literally writing it out. So this is what I've done. Let's say that this is my anthill and these are my ants. If I were really, really meticulous, I would write out each individual ant, or maybe significant divisions of ants. Like maybe, in a human population, I would divide it up as families. And this could be, the Reynoldses, and this could be the, can't come up with a last name starting with B off the top of my head, but it doesn't matter. But you see what I mean. I can break it up into systems that are important. And in addition to that, I can just describe the whole colony. I can say that this is my ant colony, or I can say that this is my nation or global community or whatever you want to call it. So there are multiple ways that I could describe my system. So what's sufficient? So let's think about our ant colony. The first case is kind of the way that things are done right now. We think about our ant colony and we think of it in terms of ants. And we describe all of the ants in the colony. We don't miss a single type of ant. If there's a new type of ant, we have to find it, we have to know what it does so that we can classify it and make it a part of our system. That's what we do when we describe things from this level. Now, it's less obvious what you would do to describe a system from the higher level. So, let's say I don't know what an ant is. I've never seen one before. I can't see ants. But I can see ant hills. I would be able to discern the existence of an ant colony by observing the mound, observing the tunnels, observing the shifting of vegetation as it disappears around the ant colony. I could see large-scale signs that an ant colony is there, and I could characterize the behavior of that ant colony using those signs without knowing about the ants. Now, I may not be able to give you an individual description of what each ant is doing, but as far as the ant colony goes, I have completely described the system. I've gotten everything that the colony is doing. That's the important thing. That's what completion means here. It means I've got all the components of the system down, leaving nothing out. Not saying anything about whether or not I have extra stuff, but if my system is only composed of R, B, and G, whatever model I have better account for R, B, and G, or the summative total of their actions as a complex system. So that's what I mean when I say that I need to have a complete description of my system. And that's very important if you're going to deal with a complex system. So let's say that I have my ant colony and it's doing something weird that I can't describe, and that I can't explain why it's happening. Like, let's say that my ant colony, when a fly flies around it, the fly just dies. If there's another component of my ant colony that has learned to build lasers, you know, ants with laser guns over here, I'm going to call it that, ants with lasers. If I don't account for that, I won't be able to give you an accurate description of the workings of the ant colony. So it's very important to pay attention to whether or not you've encompassed all of the components of your complex system. So we've established the need for near decomposability, and we've established the idea that you need to know all of the components that are significant to your system. So now I want to take a second, now that we've basically established the two things so far, or two things so far. I'm not going to say the two things. There are more things to pay attention to when you're building a complex hierarchy. But now I want to go into something else that kind of describes why I've drawn my system this way. So this is set up so that the more abstract part of the system, S, is on top. And you can see probably that I'm about to get into what I've been talking about with PM plots. Now, I've introduced PM plots as a way of plotting some arbitrary quantity P that has something to do with the organization of materials, and some arbitrary quantity M that has something to do with some characteristics about the materials that aren't necessarily the abstract organization of them. But it's really, the plot is really just a way of emphasizing the idea that those are two separate axes, you know. It doesn't necessarily have to be an exact plot per se, but it emphasizes the difference between my P and my M. So let's say that I arrange this in a way such that this axis basically represents P. So S here is more abstract, more organized than just R, B, or G. important idea behind this, an important idea is that S, R, B, and G all have to be composed of the same material. So when I move up P, material is not changing. And that comes directly from the idea that I've got a complete description of my system. S can't be composed of something that isn't contained down here, because if it were, that would mean that I had something unaccounted for. Now, we're not talking about what would happen if S was interacting with another system. What if 2 ant colonies went to war? That's not being talked about here. We're talking about, in our closed definition of a complex system, if I have made a complete description as I move up the arbitrary, as I move up the scale of abstract complexity, I guess, structural complexity is what I'm going to refer to it as, and I'll write it down. I know I wrote it down in the last one, but we're going to call this structural complexity, just to be consistent. As I move up the scale, my material isn't changing. That means that your body, as complex as you are, is still made of atoms. It's the same thing. That means that, you know, the government is still made of atoms, ultimately. It's not composed of some weird structure, some weird matter that we haven't accounted for. And that's an important thing, and it's got a lot of weight to it. Now, I need to be specific about something that is not necessarily true. As we move along this, we can be sure that M doesn't have to stay the same. That's the whole point. Maybe, like I said, maybe, you know, some ants over here have lasers, you know. These guys don't have diodes. They don't have laser diodes. They don't have, you know, a helium neon laser. But we can't be sure, we cannot be sure that P isn't changing along this axis, because these are organized differently, usually. So it's not perfect, but it does establish the idea that M does not change when you're going this way. It necessarily changes when you're going this way. Or, well, depending on what you've chosen as your axiomatic unit of material. Because if you went all the way down to the atomic level, M wouldn't vary at all moving this way. As I went from ant to ant, it's still composed of, you know, the same atoms. So, like I said, there are limits to this way of thinking, but as long as you're aware of those limits and you work inside the bounds of those limits, it's still a useful way to think. So I've organized my complex system in a hierarchy where going up in this direction increases my my structural complexity, and then in a way such that this direction is a change in the material. So later on in videos, when I actually get into something a little more conceptually involved, I know that the past few videos have been just a bunch of rambling about concepts that are not hard to digest at all. When I get into something a little more off the deep end, as long as you keep this in mind as your, you know, your basic set of concepts, you should at least be able to understand me. You won't agree with me, probably, but these are the basic ideas that I'm working with. So, once again, I've already received a few comments and remarks about the videos so far, and it's been excruciatingly helpful. It's just wonderful. So, please comment, email me, come up and talk to me if you know me. Let me know what you'd like to see, what you'd like changed. Well, within reason. You can't just tell me to stop, because I'm going to keep doing it. But yeah, if you don't do anything, I'm just going to keep talking to the camera. And like I said, I'm going to not edit this out where I walk to the camera and turn it off, because I'm a human being, and you know.